So there are three ways to calculate the rate on the ECG, right? So first we're gonna speak a little bit about the calibration on the ECG. So under normal circumstances, going upwards in millivolts, right? Two of these boxes is 1 millivolt, all right? And 1, 2, 3, 4, 5, right? Of these boxes. All right, that's 1, 2, 3, 4. Okay, that's equal to 1 second. All right, and it's millivolts over time. Okay, so based on that now, we can make some assessments, right? Or some conclusions. So 1 second is 5 big boxes. Therefore, 60 seconds is 300 big boxes. Okay, and 5 big boxes equal 1 second. Therefore, 1 big box equal 1/5 of a second, or 0.2 seconds. And if you look closely, there are in each big box 1, 2, 3, 4, 5 tiny boxes, right? So 1 big box equals 0.2 seconds. Therefore, 1 small box equals 0.04 seconds. All right, you just divide that by 5. Okay, right? So what we're saying, for example, is that if I have, oh no, like a situation like this, I'm saying that there is, so each one of these would be 0.2. So 0.2 times 2, right? So this one, so we're saying this distance is 0.4 seconds, or rather it takes 0.4 seconds to get from here to here. That's what it's really all about. Okay, so if we wanted to calculate the rate, the heart rate, that is, right, what we will be trying to say is how much of these QRS complexes would we have in 60 seconds, which is the same thing as saying how many of these would we have, how many boxes, right? So there's actually 2 boxes between each one, right? So that's 1, here to here is 2. So how many, if there are 2 boxes, right, for every cardiac cycle, then how many cardiac cycles would be in 300 boxes? That's really all it is, right? Now, there's something else I would need to add here, right? So, 1 big box, right, is 0.2 seconds, right? Okay, cool. And we have 300 big boxes is equal to 60 seconds, right? Okay, so what if we wanted to convert this into small boxes? basically you would multiply the big boxes by 5 because you have 5 tiny boxes in each big box, right? So it would be 1500 small boxes equals 60 seconds also. And what's the relevance of this? Well, basically, right? Basically, sometimes, if you're lucky, you'll have the QRS complex falling neatly like this. But what about other times? What if you have something like this, then something like this, then something, you know? Let me draw it at even, right? Okay, something like that, right? It would be more accurate to attempt to count the tiny boxes. 1, 2, 3, 4, 5, 6, 7, 8, about 8, right? Than to count the big boxes because they're not quite a whole number. Okay, and we're gonna get into that more. So in summary now, so way number 1, we can count the big boxes between 2 R waves, or better yet, between 2 QRS complexes, right? And you measure it at the peak. So count the big boxes between the peaks of 2 QRS complexes. That would be the first step. And B would be to divide 300 by the number of big boxes, right? And as we said, we're doing that because 300 boxes is equal to a minute. All right. Way number 2 would be basically the same thing, but we're using small boxes. So A, count the, that's a U, yeah, count the small boxes between 2 QRS complex peaks, and then B, divide 1500 by the number of small boxes. All right, and that would give you a similar result, but likely more accurate. All right, now before I move on, 2 major points. One, this way can only be used for rhythms that, or these 2 ways can only be used for rhythms that are regular. So for example, something that's going like this. You can't use this method for something that's like, oh, let me use a different thing, not an X this time, like a circle. You can't use it for something that's going like that. Okay, so it has to be a regular rhythm to use one of these first 2 methods of calculating the heart rate, right? Because these first 2 methods are assuming that the cardiac cycles are occurring at regular intervals. They're taking the same amount of time, so therefore you can just do a calculation and estimate how many you'd have in a minute. Versus if the cardiac cycles are occurring irregularly, that wouldn't work, right? Because some are happening faster than some, as illustrated right here. Okay. The other thing I wanted to say about especially the first method is that even though it's not as accurate as the second method, it still has some utility in being able to quickly estimate the heart rate. So for example, if I have something like this, and I have something like, let's like this, something like that, right? And I know it's one, so no, this would be one, two, three boxes and a little bit, right? I would divide 300, right? So I did the first step, which is A. I count the number of big boxes between the QRS complexes, and then I'm gonna, and I counted it to be 3, and now I'm gonna divide 300 by that number, right? Which is 3. So the heart rate would be 100. So even though, right, it's a little bit off, I could say the heart rate is approximately 100, right? It's actually a little bit slower than 100. So I could say that the heart rate is approximately 95 or something like that, right? So it's still good for reading ECGs at a glance, right? But when greater accuracy is required, then you can go ahead and use the small box method, right? Now, the other method, which is also very accurate, is to look at the rhythm strip. So then you might ask, what is the rhythm strip? Okay, so this is a normal ECG essentially. For now, you'll just have to believe me that it's normal, right? And okay, so the rhythm strip is a lead, right? Typically placed at the lower corner, the lowest aspect of the ECG, okay, of the ECG printout, and it is usually lead 2 or lead V1, right? Because those two leads tend to have, well, for lead 2, it has the best view of ventricular activity in a normal heart, and also a very good view of atrial activity, right? Or in a heart with a normal axis. And in V1, because V1 has a very good view of the atrium, so you have a good view of atrial activity. Anyhow, the rhythm strip is a 10-second strip, so it will show the electrical activity of the heart in a particular lead over a 10-second period. So therefore, if you count the impulses or the QRS complexes, right? Because remember, QRS complexes correspond with the ventricular contraction. So if you count the QRS complexes over the period of the 10 seconds, you can thereafter multiply by 6 to get the heart rate, which you would get in a full 60 seconds, right? So for example, in this case, the heart rate would be, hold on, all right. So in this case, the heart rate would be, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? And you'd multiply that by 6, okay? So that sounds like it's about 72, right? So this is a normal heart rate of 72 beats per minute utilizing the rhythm strip, okay? Okay, so here is an example of an irregular rhythm, right, for which we can again use the rhythm strip, right? So again, the rhythm strip is 10 seconds, and therefore we would count the impulses and multiply by 6 to get the heart rate, which would be the number of impulses in 60 seconds. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, and times that by 6. All right, 7 6 is 42, and 6 1s 60. So you add the 4, 102, if I'm not mistaken. You can use your calculators to double check that. But this is a high heart rate of about 102 beats per minute, right? So in summary, we went through the 3 ways in which you can check the heart rate, right? You can use the big box method, you can use the small box method, or you can use the rhythm strip. Okay, and now finally we're gonna just briefly talk about a little shortcut to get the heart rate right quickly, and then we can probably do a few examples. Okay, so let us label some boxes, right? So 1, 2, 3, 4, 5, 6, right? And we're gonna have a couple of examples. Let us say, so an X is the same as a QRS complex, okay? So in the first example, I have an X every QRS, okay? In the next one, it's every 2. This one, it's every 3. Then every 4. Then every 5. And then every 6. And for all of these, we're assuming regular heart rates, right? So what we're basically saying is, as we described earlier, that to get the heart rate, you're gonna count the number of big boxes in between each complex, right? So you're gonna pick an RR interval because you know the heart rate is regular, right? You know that the beats are occurring regularly. So you just pick 2 complexes next to each other and you check how many boxes are in between them. Of course, I didn't say this earlier, but I can say it now. If you have something like this, right? Oops. Alright. And it's regular, but some don't line up exactly. It's easiest to try to find 2 that line up, right? On a hard line. Anyway, I digress. Okay, so what we're saying is you find 2 RRs or 2 QRS complexes that are adjacent, and you check how many large boxes are between them. And after doing so, you're going to divide 300 by that number. So what we're saying is, for A, 300 divided by 1 would be a rate of 300. 300 divided by 2 would be a rate of 150. 300 divided by 3 would be a rate of 100 rather. 300 divided by 4 would be a rate of 75. 300 divided by 5 would be a rate of 60. And 300 divided by 6 would be a rate of 50, right? So we can put it down here that this is what they correspond to, right? 300, 150, 100, 75, 60, 50. So these are 6 values that you can commit to memory that will allow you to rapidly interpret an ECG. So for example, if I have something like this, a QRS complex right here and a QRS complex right here, right? So 0, 1, 2, 3, 4, 5. It's between 4 and 5, which would mean it's between 75 and 60. So automatically I know that this heart rate is somewhere between 75 and 60. So I could give it something like, okay, this patient has a heart rate of approximately 68 beats per minute or 69. It's just an approximation that allows me to rapidly interpret the ECG, especially if that is not the most concerning part of the ECG. So I'm one, rapidly able to determine if it's normal or abnormal, and two, give an approximation without doing a whole lot of calculation, for example, with the small box method, right? I would say over time, counting the rhythm strip becomes really fast as well, except for when the heart rate is really rapid. Okay, but this is just a shortcut for you as well. So just remember that each box each number of boxes in between your RR interval corresponds with a heart rate, and based on that you can approximate the heart rate just by looking at the ECG once the rhythm is a regular rhythm.